This video is about problem solving in geometry, and you'll want to start by reviewing and really memorizing or writing out the formulas and definitions in the textbook. There are lots of geometry formulas that are pretty standard, things like area, perimeter, and those of some basic shapes like rectangles, triangles, and so on. We're going to be applying some of those formulas in the following examples. For our first one, we want to find the area of a figure that is shown. Now this figure happens to be what is called a trapezoid. A trapezoid by definition has two parallel sides. In this figure shown, that would be like the top and the bottom of the figure. And then two non-parallel sides. So that would be the left and right sides of this figure. So altogether 4 sides, which makes it a quadrilateral. But by definition, one pair of those opposite sides are parallel, and the other pair of those opposite sides are not parallel. In this trapezoid that's drawn, the top side is labeled as 26 meters. The bottom side is labeled as 37 meters. Again, those are the parallel sides. The left side is labeled as 18 meters, and the right side is labeled as 21.1 meters. Now, the left side of this trapezoid is vertically straight up and down. The right side is kind of slanted down from the top to the right toward the bottom edge. And then there's another label marking the distance between these parallel sides, so the distance between the top and the bottom. Notice that it's marked with a right angle note or little square in the corner, which means that it's perpendicular to the bottom side of this trapezoid, and that height is marked as 18 meters. That's the distance between the parallel sides. So in order to find the area of this trapezoid, of course, we're going to have to bring in the formula for the area of a trapezoid, which could be written as A equals 1/2 H, open parenthesis, B1, B subscript 1 that is, so B sub 1 plus B sub 2. Now let's discuss briefly what these pieces mean. So A stands for area, that's what we're looking for. H stands for height. Now height, as defined by a trapezoid, is the distance between the parallel sides. So in this case, that would be the 18 as labeled. We can start to rewrite this formula, but start plugging in the numbers we know. So instead of H, we're going to substitute the value 18. And then moving into the parentheses here where we see B sub 1 plus B sub 2, those bases happen to be the parallel sides of the trapezoid. So in this case, B1 and B2 are like the top and the bottom. Now it doesn't matter which one you call B1 or B2, so we'll just pick I guess the top to be B1, so I'll put 26 for that, and B2 I'll make the bottom, so 37 for that. Again, you could switch those and you will not get a different result. Now all we have to do to find the area is simplify this arithmetic. Of course, this turns into, if you just crunch these out here, 1/2 times 18 is 9, and then inside the parentheses you have 26 plus 37. If you add that up and multiply it by 9, altogether a calculator should help you get 567. And then for area, we wouldn't just put m for meters because that's the unit given for all these lengths. Area is always square units, so we're going to put meters squared as our final area result. Let's try another example. This one says we want a triangle has a base of 6 feet and an area of 30 feet squared. Find its height. So in this case, they're telling us we have a triangle. We'll go ahead and draw one with the following specifications. It says it has a base of 6 feet and an area of 30 feet squared. Find its height. Now actually, okay, a picture may not even help us out too much because this is really going to just work with the formula itself. Let's just bring in the formula for now. I'll explain why a picture may be more trouble than it's worth in a second here. But let's write out, first of all, the formula for area of a triangle. And by the way, we know we're looking for that because this problem actually specifies we have a triangle and it gives us something about the area in it. So area of a triangle is 1/2 times base times height. Now, as you can see in this problem, they're actually giving us these measures. The base is 6 feet, and the area is 30 feet, and then they say find the height. So you can see all the corresponding measures here. What we want to do is plug in the values we know. So if base is 6, then we're just going to rewrite this equation, but instead of b, I'll put 6 in parentheses. And if area is 30, then instead of a, I'll put 30. Notice that that leaves the h variable with nothing to plug in, but that's what we're trying to find. So this will work out well where we can just solve for h. If we rewrite this, we'll have 30 equals, on the right side we have 1/2 times 6, that's really 3. So we have 30 equals 3h. Of course, to get h alone, we'll divide by 3 on both sides, as we've seen with equation solving by now. And so let me kind of recopy things up here. On the left side we have 30 over 3, that's really 10. So 10 equals, and then on the right side we have just the h because we got rid of those 3's. So h equals 10. Now they say find the height, so we should say probably 10 feet, consistent with the units given in this problem. Notice that in this problem we solved it just doing algebra, really, using the formula. There was no need for a diagram or a picture. And I mentioned I would say why it's not as helpful to draw one. The problem with the triangle diagram is there's so many ways to draw it. You could draw a right triangle with slant side on the right, a right triangle with slant side on the left. You could draw a non-right triangle. All these variations will kind of differ in how you label it, given the measures in this problem of base and height and area. So since we don't even need them to do the algebra of solving for h, it's better just not even to draw it. Let's try another example. This one states a rectangle has a width of 46 centimeters and a perimeter of 208 centimeters. Find its length. So once again, if you are familiar with all the formulas given in a chapter of this content, where they'll just list a whole bunch, typically in a textbook, area, perimeter, volume, things of that nature. In this case, we're talking about the perimeter of a rectangle, and there's a formula for that. So just to bring that in here, P equals 2 times length plus 2 times width. So that's something we'll have to just remember or memorize and know to bring into the problem here. Now it says that a rectangle has a width of 46. So we can replace W of width with 46. And it says it has a perimeter of 208. So I can replace P with 208. I'm going to copy 2L down. We don't have anything for that yet. And then instead of W, so instead of plus 2W, I'll put plus 2 times 46, since that was given. Notice the question is asking us to find the length, and that's the only variable we have left in this expression that's not solved. So we can do so by just getting L alone here. So let's go ahead and rewrite this again. We'll have 208 on the left side equals 2L plus, we had 2 times 46, really that's 92. We'll replace that, and then we'll go ahead and subtract 92 from both sides. On the left side, 208 minus 92 will give us 116. On the right side now we just have 2L. And so we can get L alone by dividing by 2 on both sides. Those 2's will cancel on the right side now, leaving us with L equals 116 divided by 2 would end up being 58. And then, of course, our units given in this problem way above, we know are centimeters because that's what they said the width was, 46 centimeters. And so we can say the length must then be 58 centimeters. And so there's our length as requested. Let's try another example. This one asks us to find the area and their circumference, and then there's a diagram of a circle, and in that diagram the distance all the way across the circle through the center of it is labeled as 40 feet. So it's important to understand what pieces of a circle are involved in its formulas. And so just as a recall or refresher on the definition here, the distance from the center of the circle to anywhere on the outside of it is known as the radius. So you might see it labeled as r. But the distance all the way across, so that would be like if you put two radii together, spanning all the way across, that makes up the diameter. And so you could say, that's why I said in this case, the diameter is given as 40 feet, and usually the diameter is labeled kind of right in the middle above the center there. Now we want to find the area and circumference, which means we're going to have to bring these formulas back to life here. The area of a circle is pi r squared, where r is radius. And the circumference of a circle actually has two different formula options. One of them is pi d, pi times diameter, or another one is 2 times pi times r, which is actually the same thing because 2 times r is d. That's the diameter, as we said in the description of those different pieces. So with those formulas brought into the right context here, all we have to do is plug in our numbers. Now, if 40 is labeled as the diameter all the way across, we could say that the radius would be half of that, which would be 20. And of course, the units here are in feet. We'll make sure that we include that for our answer. But if the radius is 20, that means I could say area equals pi times 20 squared, just plugging in 20 for r as radius, which means if I just crunch out 20 squared is 400, which means the area would be 400 pi. Now, pi is what's called an irrational number, and it's approximated typically as 3.14, but we want to leave this as an exact answer without approximating it, because as soon as you approximate pi is 3.14 and then multiply that by 400 in this case, you're going to have to round your answer and it just gets less accurate. So unless a problem is requesting some kind of rounded value, we're just going to leave the exact answer. So 400 pi. Now if this is an area measure, we should say feet squared for its dimensions. Now circumference, as mentioned, is 2 times pi times r, or pi d, same thing. And so if we plug in the value we have for r here, we would end up with 40 pi. Or you could plug the value for d in the pi d formula, same thing, 40 pi. And again, this will be feet, but a circumference is more of a linear measure, even though it's kind of curving around the circle or the distance around it. It's still considered a linear or straight line kind of measure. And so we'll leave it just as 40 pi feet. And yes, we're going to leave the pi in there in the same way that we did for area for an exact answer. Let's try another example. This one gives us the picture of a three-dimensional box, and we're asked to find the volume of it. Now this box is labeled with the distance all the way across the bottom of it as 5 centimeters. We might consider that the length, if it's all the way across the bottom of it. The distance top to bottom is labeled as 3. We might call that the height. Let's label it as h for height. And then this box being three-dimensional has a depth, or you could call that the width, and that's labeled as 3 centimeters. And so to find the volume, we'll have to just bring in the formula for the volume of a box, which happens to be length times width times height. So of course, conveniently, we have all those measures. All we have to do is substitute them and multiply together. We said length was 5, width we labeled as 3, and height we also label as 3. It's worth mentioning that the way you label a box, as far as which side is the length and the width and the height, doesn't actually matter, because you could flip this box around and it's not going to change the actual measure of the volume, but it might change your preference on which side to label which. So you could even switch the length and the width or the height and you'll get the same result. So we see here volume is really just 5 times 3 times 3, which ends up being 45. Now, the units for this box are given in the diagram as centimeters, so we'll put centimeters after 45, but then volume is always cubic units, so really we have to say 45 centimeters cubed, which is just a power of 3, written right up above the cm as that superscript there for the power of centimeters. Let's try yet another example. This one says find the volume, and then we're given a diagram. This time it's of what's called a cylinder, which is a circular object that's kind of flush, flat with the ground, but standing upright. So think of like, a roll of paper or paper towel or something like a cardboard roll. It looks like that, standing vertically, and we have a couple labels on it. The height of this cylinder is 8 centimeters. And then the radius of the top and bottom, both being circles, is labeled as 6 centimeters. Now we want to find the volume of this cylinder, which again requires us to bring in that formula. So the formula for the volume of a cylinder is the area of one of its bases, which is the circles, times the height. Well, if the bases are circles, we already discussed the area of those above, that would be pi r squared, and then times the height would be times h. So pi r squared h will give us the volume of a cylinder. Of course, we have the labels that we need in this diagram, so we'll go ahead and substitute them in and rewrite v equals pi times, now r was given as 6, so we have 6 squared, and then h is 8, so pi 6 squared 8 is how we put those all together. Of course, we'll actually crunch those numbers out. 6 squared is 36, 36 times 8 should end up being 288. Now we're going to leave the pi in there like we've been doing to give an exact answer. Instead of multiplying 288 by 3.14, which would require us to round and therefore be a little bit off compared to the actual theoretical answer, we're going to leave this in that exact form, 288 pi, and then we can use our units as centimeters. Now if it's volume, like we saw previously, we need to cube the unit, so it's centimeters cubed for the volume of this cylinder. Let's try another example. This one is asking us to find the volume, and then we have a cone given in a diagram. So a cone, it's just like an ice cream cone, one of those nice pointed on one side and open and circular on the other. But this cone is kind of flipped upside down, I guess you could say, so the point is on top. And it's labeled with a height of 16 meters. And then the radius of the circle, which is acting as the base of this cone, the open circular side kind of laying flat down on the ground, that's labeled as 5 meters, the radius of that circle. So we want to find the volume of this cone, which is going to require us to bring in the formula for that. Turns out volume of a cone is equal to 1/3 times the volume of the cylinder in which it would fit. And we just kind of reviewed that above. So we have 1/3 times pi r squared h. The pi r squared h being the volume of the cylinder in which this cone would fit exactly. The 1/3 accounts for the fact that a cone is only 1/3 of the volume of that cylinder. So if we plug in the appropriate measures, we end up with 1/3 times pi times 5 squared, 5 being the radius, times 16, that being the height. And then if we put this in exact form, we should end up with a fraction, 400/3 times pi, and then the units, of course, are meters cubed, cubed being for volume in this case. Let's try another example. This one's asking us to find the complement of 41 degrees. Now that's a geometry or trigonometry vocabulary word here, and so that would be listed in one of our definitions in the textbook. And I'm just going to review or remind you that a complement of an angle is what else it would take to add up to 90 degrees. So we can find out what that is by, in this case, if we want to find the complement of 41 degrees, I can find out how much more I would need to add to 41 to get to 90 by simply subtracting 41 from 90. So if I do 90 minus 41, I'll end up with 49 degrees, and that would count as the complement of 41 degrees, because if I add those two together, 49 and 41, I get 90 degrees. Our next example says an angle's measure is 78 degrees less than its complement. Find the angle. So we're using that word complement again, same definition, but this time the problem is set up a little bit differently. It says an angle's measure is 78 degrees less than its complement. Let's first of all give a name for the angle's measure. Why don't we just call that measure x? You could use m, doesn't really matter, just some kind of variable. If an angle's measure is 78 degrees less than its complement, we can translate that into an algebraic equation where we say x, that's an angle's measure, that's equals 78 degrees less than its complement. Okay, so 78 degrees less than would mean we're subtracting 78 from something. What is the something? Well, its complement. So now we have to understand, really from the previous example, how to find the complement of an angle whose measure is x. What we did previously was just subtract the angle from 90 to find the complement, so we can do the same thing here, except this time we have a variable. So we'll say x equals, and then 90 minus x would be the complement of x. That's subtracting it from 90. If we take a look at this algebraically, we can combine some like terms and rewrite this as x equals, and then on the right side I have 90 minus x in parentheses, and then after that I have minus 78. Really all we need to do is get x alone, and so these parentheses become unnecessary. I could rewrite this as 90 minus x minus 78, which means I have x equals, now we can subtract or combine these like terms, 90 and minus 78. Of course that would give us 12, so we have x equals 12 minus x, but then to get x alone I could add x to both sides. Remember, variables first, smaller to larger and something like this after combining like terms. So the x's on the right side cancel out, leaving us with 2x on the left equals 12. We bring this up and redo this here. If I have 2x equals 12, I could solve for x simply by dividing by 2, which will give us x equals 6. Now remember the units of what's going on here. We're trying to find an angle measure, and they were given above in degrees here. So we'll say 6 degrees for this angle measure.